Hi, my name is Leandro. I will present this paper today using machine learning and in-band network telemetry for self-symmetric estimation. Here we have some topics that we'll talk today. The first presentation, objectives. Next, about the motivation, the problem statement, the proposal and the evaluation, the results, and the conclusion and future directions. Here we have some important points. What is expected by the end of this presentation, some takeaways. First, understand that the network administrators, the network operators have some difficulty in compute the QoS on their networks. Understand how INT enables the collection of the data regarding networks operation at a level of granularity never achieved before. Understand how INT metadata can represent the state of the network. Understand how INT metadata can feed machine learning algorithms for QoS estimations. And note that it's possible to get better results for QoS estimations using INT to feed machine learning rather than classic metrics like RTT, jitter, CPU usage, memory usage, and understand how the network edge provides more information about the QoS. So, we have a good question. From the network operator's point of view, the current SLA, the current QoS is violating the SLA? Yeah, yes or not? It's an important question. Regarding this, the self-symmetric estimation, it's a good point to answer these questions. With programmable networks and INT, we have a lot of data, a lot of fine grading metrics, and machine learning are hungry for data. So we can use these two powerful tools for self-symmetric estimation. Regarding this problem, regarding this scenario, we designed three research questions. First, can INT metadata can use it to feed machine learning algorithms? Two, is it possible to obtain a better estimation of self-symmetrics using INT and ML? If so, how accurate is this estimation? And three, what is the best machine learning method to work with INT? So we have three good questions to driving our paper. In our work, we have one central idea, that is, we analyzed how INT metrics, called dataset X, correlate with QoS metric data, called dataset Y, and the evolution of the metrics X and Y is treated as a time series. Our hypothesis is that variations in self-symmetrics like frames per second from a video service have a positive correlation with INT metadata. Our machine learning models will compute one function that we are use the name y hat. That y hat is a function of approximation of the function y, or of the real QoS metric, and the y hat is the predicted QoS from our machine learning models. Here we have our scenario. Yeah, we have a dash video service. In this server, we have one video with three resolutions, three configurations, and the client can consume this video according to the load on the network. The client can make transitions on the same video according to the loads. If the load is high, the client will consume the video, will watching the video in the lowest resolution. If the load is not high, the client will consume the video in the right resolution. We have the three load generators that will consume other videos. We have one load generator microburst that will create a noise in this network. And in the edge node, we have one sync server that will receive the int metadata to prepare to the machine learn algorithms. About the design of experiment, we have some pieces. First, MPEG-server hosting videos in different resolutions. Client consume videos according to the network load. Load generators consume videos according to the load partners. We use the sinusoid, flashcrowd, and mix. Sinusoid and flashcrowd together. The microburst generator creates noise in the network. Telemetry flows get int metadata from the BMV2 suites. About the duration, the experiment lasts approximately 19 hours, 8 for sinusoid, 6 for flashcrowd, and 5 for mixed load. Regarding the machine learning models, we use decision tree, random forest, neural networks, and k-nearest neighbors. To evaluate our machine learning models, we use the NMAE error. The NMAE error is a difference between the real QoS computed on the client and the estimation computed from our machine learning models. Here we have some video parameters. We have the same video in 3 resolution, and we have 2 configurations about the audio metric. Here we have the equations for sinusoid, the equation 1, and equation 2, 3, and 4. These equations are to flashcrowd load because the flashcrowd have 3 phases, 3 different phases: hump up, sustained, and hump down. In the table, in this slide, we can observe the parameters used in our experiments. About the results, here we can observe the histogram about the frames per second collected and the percentage. And we can observe in the mix data set, we can see that in the most of time in our experiment, the client consumed the video in the lower resolution because 30% of the time, 50% of the time, the client consumed the video in lower resolution, and the sinusoid and the flashcrowd more balanced data set. So, about the NMAE error, this is an error, the lower the better. We can observe how our machine learning models perform in 2 different situations. First, individually, we train and we evaluate our machine learning models in the same data set. We split our data set to training, to test, and to evaluate, but using the same load, just sinusoid, just flashcrowd, and just mix, and we can observe that the random forest is the best of all. And sinusoid dataset, in flashcrowd dataset, in mix dataset. And we want to evaluate our machine learning models with cross evaluation. For example, we train our models in sinusoid dataset, and we evaluate our models in the other load partners. And we can observe that the results not so good, but is an important information to share in our paper. Here we have two results in this graph. This graph represents the gene importance. The lower the better. We can observe that the metadata that brings from the machine learning model more precision information is the QL depth. The QL depth is in our experiment, in our study, the QL depth metadata is the metadata that have a good point of view about the QoS metric, about the estimation, the QoS metric. And we can observe too that in the edge node, the node more close to the client, we have more accurate information, more precision information about the QoS estimation. Here we have some contributions in this paper. First, propose and evaluate the joint usage of machine learning and INT for dash metrics estimation. Analyze different machine learning algorithms and show which method obtain better results. Review which network metric and which network equipment mostly influence machine learning algorithms. About the challenges and the future directions, we have some points. First, amount of metadata collected. We know that it's a lot of data, but in this research, in this paper, in these experiments, we decided to collect the all data from the INT specification because we was just analyzing this case. But of course, in the real network, we can observe, we can analyze more which metadata we will collect. The other point is about the collect rate. This is so important from our research because if we change the collective rate, we change the result from the NMAE error. And the last, about the topology covering, is the other challenge because in our experiment, we have a very simple topology, just 3 nodes. In the real network, we have a lot of nodes, and we will need a lot of telemetry flows to collect a lot of metadata to train our machine learning models. This is it. Thank you. Questions now.